Hi, how's everybody doing? We're going to talk. I'm moving myself. Yay, hang on. All right, that's better. We're talking about atoms and atomic theory today. So, what is our essential question? It was already on the board, but in case you're watching the video at home, you're rewatching it. The essential question is how and why has the atomic theory changed over time, and how can we describe the molecular motion of the states of matter? That's what we're going to be talking about in this video that you're watching both live in class today and you'll watch it tonight for homework to make sure that you get all the information. Okay, so let's move forward. So your ICANN, we've already talked about this, explain, this is in class, but again, if you were watching this for the second time, explain that atoms are the smallest unit of an element and are composed of subatomic particles, and analyze models of the scientific theory of atoms. So that was your do now from earlier today. So let's talk about atomic theory and how it has changed over time. We're going to start with Dalton's theory here and move all the way forward till we end up in today's with wave theory. Now, in class, if you were in the long class period on Friday, you got this graphic organizer. You got that, and you cut it out and you put it in your ISN. Now, you were supposed to have done some research, but I have a sneaking suspicion some of you didn't. So we're going to do that today in class. Also, for those of you that are just joining me today, you've just gotten this particular cutout, and so you'll be ready to begin. So let's get started, shall we? As we talk about atomic theory and its changes over time. So because we can't see atoms, we use models. We always use models to teach and learn about atoms because we can't see them. They're teeny tiny. And theories have changed over time because, well, technology's got better. We can see better. And so as we build on the past, it helps us to understand, and we build on past research and experiments. So the whole idea of this class is to show you, or this particular lesson, is to show you how we started way back in the past and come forward to kind of see how the atom and the way we view it has changed. So let's go back 2,000 years ago to a Greek philosopher by the name of Democritus. Now, he theorized that everything that we see was made of these invisible particles called atoms, or in the Greek, atomos. Now, what we know about Democritus, we get from his enemies, people that didn't like him. We kind of like your haters telling everybody what we know about you. But he was a contemporary of Socrates, and Socrates called him a quack. This is what he said, that the smallest part of matter is an atom, and the atom is indivisible. They're small, hard particles that are made of the same material, but were different shapes and sizes. Like, for instance, he thought water was kind of slippery and pointed. That's why water looked the way it does. His model had empty spaces between the atoms, so there was nothing there, and he didn't account for any subatomic particles. So his model will hold for 2,000 years until 1803, when John Dalton, who's a chemist, and he's a teacher, he began to study in weather and color blindness and gases. And as he began to really study, he understood there was something there, something much smaller. So in 1803, he develops his model of atomic theory. This is what he comes up with: that all elements are made of atoms which are indivisible and indestructible. So the atoms were they were. On the periodic table, if you remember that he has all kind of divided up, all the atoms in the noble gases were the same, and they couldn't change. The ones in the metals were all the same, but they were different from each other. So atoms of the same elements are the same, different atoms are different, and the compounds are formed by joining these atoms. So here's his model. Very circular, very easy to understand. You have the nucleus, proton, neutron, and we're moving on. Again, he didn't account for any subatomic particles. His model will stand real well, and it'll be right in place until about 1897, when Joseph John J.J. Thomson came up with the plum pudding model. In this little model, he discovers electrons, and he'll win some awards over this one. He used a cathode ray tube, and he bombarded it with light energy, and he began to see that there was smaller particles that make up atoms. So he kind of got the model of looking at plum pudding. I've never eaten plum pudding. I've never seen plum pudding, but apparently it makes a great model. And he says the atoms of pudding, the stuff that's the pudding, is positively charged materials. And throughout this pudding are a negatively charged electrons. And it looks something like this. So here's the pudding, and here's all of the the positively charged particles. And in the midst of them are these little negatively charged electrons. They're just kind of hanging out in there, enjoying where they are. His model will hold until about 1897. Again, the problem with this one, it didn't account for the structure, or the, I made a mistake there. Let me get that put in for you. Didn't account for the structure, and this is why you don't leave your notes out where you can't find them. Didn't account for the structure or for neutrons. So he didn't have an idea of the way things are put together, and he didn't account for where the neutrons were. And his will hold from 1908, but not as long as the other ones, because he has to give it up in 1913 to a man by the name of Ernest Rutherford. Ernest Rutherford uses what's called the gold foil experiment. He bombards gold foil with atoms, with just various sundry atoms. And he realizes that the atom has a nucleus with a positively charged particles that are scattered around the outside of its nucleus. He didn't account for neutrons or electron orbits, and so it will look kind of like this. So here's your nucleus. You have a neutron, you have a proton, you have these orbits, and you have electrons. So here's where the particle went. They fired off the electrons. It hit, some of it went through the gold foil, and some of it bounced or came straight back. What it showed him was that they had a positive charge within the center of the atom. But it also came up with what you could not predict, which is called the Heisenberg uncertainty principle. You don't need to know that, but just know that it's there. Okay? So this experiment changes the way we viewed the atom. It'll hold from 1913 and will be what we consider the gold standard until Bohr came along and said, nope, they move in orbits around the nucleus like that does the sun. Now, he didn't account for neutrons, and he simplified too far electron orbits. He didn't take into account that they may not be as nice and neat as he put them. So he went from the little fly-out thing that we saw in Rutherford's model. Bohr's model says, nope, these are shells, and they have energy levels. So this is 1 time, 2 time, 3 time. And so you begin to see you have 2, then you have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. And the farther shell out was the one that will gain or lose electrons when you create a compound. Don't need to know that yet, but just bear that in mind. So you go from that to this very structured model, and it holds. This model will hold, and people will use that from 1913 all the way in 1932, when James Chadwick will discover the neutron. That changes the way they view what goes on inside the atom. And then de Broglie just realized that the positively charged nucleus has an electron orbit, which is the electron cloud, which we talked about in the structure of the atom. So what we call wave theory. So here is Bohr's model. Again, the shells, your nucleus, and all the things that go on here. But what we've now discovered is that, yes, you have the shells. So here's the shells, 1, 2, and 3. But they aren't circular. They're kind of wavy. So here's one of the shells, and it's just going in and out. Here's the other shell. And these little areas, these wave axes, are called your electron clouds. It's where your electrons hide. So electrons are not orbit in the nucleus in a neat planet-like orbit, but they move at high speeds in this electron cloud around the nucleus. Now, let's talk about what you're going to be doing for my class. So, let me make myself a little bigger so you can see me. Hello. All right. On Friday, the first period class took a quiz on how to find neutrons. Now, the second class, you have the same quiz, but yours will be a homework assignment, and it will be posted in exactly how I want you to do it, and there'll be a video to attach to it so that you can go back and watch it again, so that you know what you're doing. Both classes on Friday are going to have a quiz over the things that you put in your ISN and on how we come up with neutrons in our models. So be aware, these videos will be online on the 100 Academy website. You can video them and watch them again at your leisure. First period, your homework will only be working on this. Third period, your homework will be to do the atomic, find the neutrons, and also working on this. When each of you come to class, I will be checking. All right? All right, have a good night, have a good day, and we'll talk to you later. All right, bye.